Dirichlet's transformation of numbers into a deep, structured science marks one of the most important turning points in the history of mathematics. Before his time, numbers were often treated as objects for clever manipulation rather than as elements of a unified theoretical system. Number theory, in particular, was admired for its elegance but viewed as a collection of isolated puzzles. Mathematicians solved problems about primes, divisibility, and equations using ingenious tricks, yet there was little sense that these results belonged to a single, coherent framework. Dirichlet changed this perspective forever by showing that numbers could be studied with the same rigor, depth, and structure as geometry or analysis. To understand the magnitude of his achievement, it is important to recognize the mathematical climate of the early 19th century. Many results in number theory were known, some dating back to ancient Greece, but they were disconnected. Proofs often relied on intuition or special constructions, and there was no common language to unify them. Dirichlet believed that mathematics should rest on firm logical foundations. For him, numbers were not just symbols on a page. They were objects governed by precise laws that could be revealed through rigorous reasoning. This belief drove his work and reshaped how mathematicians approached numerical problems. One of Dirichlet's most revolutionary ideas was the introduction of analytical methods into number theory. Analysis, which deals with limits, functions, and infinite processes, was traditionally considered separate from the study of integers. Dirichlet saw no such boundary. He realized that by examining how functions behave, one could uncover deep truths about numbers themselves. This insight culminated in his famous theorem on arithmetic progressions, which proved that every arithmetic sequence with coprime first term and difference contains infinitely many prime numbers. The result itself was stunning, but even more important was the method. Dirichlet used tools from analysis, such as infinite series and complex functions, to solve a problem purely about whole numbers. This fusion created an entirely new way of thinking. Through this work, numbers stopped being isolated entities and became part of a broader analytical structure. Dirichlet introduced what are now called Dirichlet characters and Dirichlet series, abstract objects that encode numerical information in functional form. These ideas allowed mathematicians to study numbers indirectly by analyzing the properties of functions associated with them. This shift was profound. It showed that the behavior of primes and integers could be understood through patterns, symmetries, and structures that exist beyond simple counting. Equally important was Dirichlet's insistence on precise definitions. Before him, mathematicians often relied on vague notions, especially when dealing with functions. Dirichlet demanded clarity. He provided one of the first modern definitions of a function, describing it as a rule that assigns a unique value to each input, regardless of how irregular that rule might be. This definition may seem obvious today, but at the time it was groundbreaking. It allowed mathematicians to handle functions that were discontinuous or complex, expanding the scope of analysis and making it applicable to number theory in a rigorous way. By enforcing strict logical standards, Dirichlet transformed mathematics into a more disciplined science. Proofs were no longer judged by elegance alone, but by completeness and precision. This approach brought number theory out of the realm of mathematical curiosity and placed it at the heart of pure mathematics. Problems about numbers could now be tackled systematically, with general methods rather than ad hoc tricks. The field gained internal coherence, making it possible to build new results upon old ones with confidence. Dirichlet's influence extended beyond his own discoveries. His methods inspired later mathematicians to search for hidden structures within numbers. Bernhard Riemann, for example, expanded Dirichlet's ideas into the study of the z, a function, leading to one of the most famous unsolved problems in mathematics. None of this would have been possible without Dirichlet's initial step of linking numbers to analytical structures. In this sense, he did not merely solve problems. He changed the direction of mathematical thought. What makes Dirichlet's transformation so remarkable is that it was driven by philosophy as much as technique. He believed that mathematics should reveal universal truths through logical necessity. Numbers, in his view, were not arbitrary creations of the human mind, but elements of an ordered system waiting to be understood. By uncovering the structures underlying numerical relationships, he gave mathematicians a new sense of purpose and possibility. This transformation also affected how mathematics was taught and communicated. As a professor, Dirichlet emphasized clear reasoning and conceptual understanding. He encouraged students to think in terms of structures and general principles rather than memorizing procedures. This educational legacy helped spread his approach across Europe, shaping generations of mathematicians who carried his ideas forward. In the modern world, Dirichlet's transformation of number theory continues to resonate. Fields such as cryptography, computer science, and mathematical physics rely on concepts that trace back to his work. The idea that numbers can be studied through abstract structures and functions is now fundamental. What was once seen as a playground for clever minds has become a central pillar of modern science and technology. Ultimately, Dirichlet turned numbers into a language of structure, order, and deep interconnection. He showed that beneath the surface of simple integers lies a rich and intricate world governed by precise laws. By bringing rigor, analysis, and abstraction into number theory, he elevated the study of numbers to a true science. His work reminds us that the greatest breakthroughs often come not from finding new answers, but from discovering new ways to ask questions and understand the hidden structure of reality itself. Dirichlet's groundbreaking ideas that shaped modern mathematics and physics represent a turning point where abstract thought began to influence not only pure theory, but also the way the physical world is mathematically understood. His genius lay in recognizing that mathematics is not a collection of separate subjects, but a unified language capable of describing patterns in numbers, space, and nature itself. Through his ideas, Dirichlet built bridges between disciplines that were once considered distant, and those bridges still support much of modern science. One of Dirichlet's most influential contributions was his work on functions and their behavior. Before him, mathematicians often assumed that functions were smooth, well-behaved expressions, usually representable by formulas. Dirichlet challenged this assumption by expanding the concept of a function to include far more general and even irregular cases. By defining a function as a rule that assigns a single value to each input, regardless of continuity or smoothness, he laid the groundwork for modern analysis. This idea fundamentally changed mathematics because it allowed mathematicians to rigorously study phenomena that were previously considered too chaotic or undefined. This shift had enormous consequences for physics. Physical systems often involve discontinuities, sudden changes, and boundary effects. Dirichlet's broader definition of functions made it possible to model such systems mathematically. His ideas helped formalize the mathematical tools used in heat conduction, wave motion, and electrostatics. In particular, what are now called Dirichlet boundary conditions became essential in solving differential equations that describe physical processes. These conditions specify the values a function must take on the boundary of a region, a concept that is central to modern physics and engineering. Dirichlet's work on Fourier series further illustrates his impact. Fourier had proposed that functions could be represented as sums of sine and cosine waves, but the theory lacked rigorous foundations. Dirichlet provided the conditions under which Fourier series converge and accurately represent functions. This was not merely a technical improvement. It transformed Fourier analysis into a reliable scientific tool. Today, Fourier analysis is used everywhere, from signal processing and medical imaging to quantum mechanics. Dirichlet's insistence on rigor ensured that these applications rest on solid mathematical ground. In pure mathematics, Dirichlet's ideas reshaped analysis and number theory simultaneously. His introduction of Dirichlet series connected infinite sums to deep numerical properties. These series became powerful tools for studying prime numbers and arithmetic structures. At the same time, they influenced complex analysis, leading mathematicians to explore functions of complex variables in greater depth. This interplay between numbers and functions became a defining feature of modern mathematics, and it originated largely from Dirichlet's vision. Another aspect of Dirichlet's genius was his emphasis on general principles rather than isolated results. He was less interested in solving individual problems than in discovering methods that could solve entire classes of problems. This approach influenced how mathematics evolved in the 19th century. Instead of accumulating disconnected theorems, mathematicians began building theories, coherent systems governed by clear axioms and logical relationships. Dirichlet's work exemplified this shift and inspired others to follow the same path. His influence on later mathematicians cannot be overstated. Bernhard Riemann, one of the greatest mathematical minds of all time, was deeply shaped by Dirichlet's ideas and teaching. Riemann's work on complex analysis, geometry, and number theory grew directly from foundations Dirichlet helped establish. Even concepts that dominate modern physics, such as the mathematical structure of space and the behavior of waves, can be traced back to this intellectual lineage. In this way, Dirichlet stands at the root of ideas that eventually influenced Einstein's theories and modern theoretical physics. Dirichlet's impact on physics is also philosophical. By showing that abstract mathematics could precisely describe physical reality, he reinforced the idea that the universe is governed by mathematical laws. His methods demonstrated that rigor and abstraction do not distance mathematics from reality, but bring it closer to truth. This belief encouraged scientists to trust mathematical models, even when they seemed removed from immediate physical intuition. Many breakthroughs in physics followed this path, relying on mathematics that initially appeared purely theoretical. Equally important was Dirichlet's role as a teacher and intellectual leader. His lectures were known for their clarity and depth, emphasizing understanding over rote calculation. He taught students to think structurally, to seek the underlying principles that govern complex phenomena. This educational influence helped spread his ideas throughout Europe, shaping the development of mathematics and physics for generations. Through his students and colleagues, Dirichlet's approach became part of the scientific culture. What makes Dirichlet's contributions truly groundbreaking is their lasting relevance. Modern technologies depend on mathematical tools he helped legitimize. Digital communication relies on Fourier analysis. Engineering simulations depend on boundary conditions inspired by his work. Theoretical physics continues to use functional analysis and differential equations that trace their lineage back to his ideas. Even when his name is not mentioned, his influence is present. In essence, Dirichlet reshaped modern mathematics and physics by redefining how problems are approached and solved. He showed that abstraction, when guided by rigor, unlocks powerful insights into both numbers and nature. His ideas did not merely add new knowledge, they transformed the very framework within which knowledge is created. By uniting analysis, number theory, and physical applications, Dirichlet helped create the modern scientific world, one in which mathematics serves as the universal language of understanding. The quiet genius behind concepts every mathematician still uses today is one of the most remarkable aspects of Dirichlet's life and work. Unlike many celebrated figures whose names dominate popular science stories, Dirichlet's influence operates silently, embedded deep within the foundations of modern mathematics. His ideas are so fundamental that students encounter them early, often without realizing they are stepping into a framework shaped by his mind. This quiet presence is not a sign of obscurity, but of true greatness. His concepts became so essential that mathematics itself could no longer function without them. Dirichlet was not a mathematician who sought attention or dramatic breakthroughs designed to impress the public. His strength lay in refinement, clarification, and deep structural thinking. He took existing ideas and reshaped them into precise, usable tools that could support entire theories. This is why his legacy is woven into everyday, mathematical language. When mathematicians speak of functions, convergence, boundary conditions, or rigor, they are often unknowingly echoing Dirichlet's approach. One of the clearest examples of his quiet genius is his modern definition of a function. Before Dirichlet, functions were often thought of as formulas or smooth curves. This limited view excluded many useful mathematical objects. Dirichlet challenged this assumption by defining a function as any rule that assigns a unique output to each input. This simple but radical idea allowed mathematics to move beyond neat expressions and embrace more complex, even irregular, behavior. Today, this definition is taken for granted. Every student learns it early, yet few realize how revolutionary it once was. Without this concept, entire branches of modern mathematics and physics would simply not exist. Another deeply embedded contribution is the idea of rigorous convergence. Infinite series and processes were used long before Dirichlet, but often without clear justification. Mathematicians trusted intuition, sometimes leading to errors or contradictions. Dirichlet demanded proof. He carefully established conditions under which infinite sums, such as Fourier series, truly represent functions. This insistence on rigor transformed analysis from an intuitive art into a reliable science. Today, whenever mathematicians check whether a series converges or whether an approximation is valid, they are following principles Dirichlet helped establish. Dirichlet's name also appears in many concepts that are now routine tools rather than celebrated discoveries. Dirichlet boundary conditions, for example, are used whenever differential equations model physical systems. Engineers, physicists, and mathematicians apply these conditions daily, often without reflecting on their origin. Yet this idea captures Dirichlet's genius perfectly, a clear, precise way to connect abstract equations to real-world constraints. By specifying values at boundaries, complex physical problems become solvable. This approach quietly underlies technologies ranging from bridge design to medical imaging. In number theory, Dirichlet's influence is equally subtle and profound. His methods introduced a level of structure that still defines the field. Modern number theorists routinely use characters, series, and analytical tools that trace directly back to his work. These concepts are now standard, almost invisible in their familiarity. But at the time, they represented a dramatic shift in how numbers were understood. Dirichlet did not merely solve problems. He created a language in which future problems could be expressed and solved more naturally. What makes Dirichlet's genius particularly striking is the balance he achieved between abstraction and usefulness. His ideas were abstract enough to unify entire fields, yet concrete enough to be applied repeatedly. This balance is rare. Many mathematicians excel in abstraction but struggle with applicability, while others focus on computation without deep theory. Dirichlet bridged this gap. His concepts were not flashy, but they endured because they worked. Across problems, disciplines, and generations. Dirichlet's personality mirrored his mathematics. He was known as reserved, thoughtful, and focused on substance rather than show. He did not flood journals with papers, but each contribution carried immense weight. Colleagues respected him not for bold claims, but for the reliability of his results. When Dirichlet published something, it was trusted. This reputation reinforced his quiet authority within the mathematical community. As a teacher, his influence multiplied. Dirichlet did not simply present results. He demonstrated how to think. He emphasized logical structure, careful definitions, and conceptual clarity. Students learned not just mathematics, but a disciplined way of reasoning. This teaching style shaped future giants of mathematics, including Bernhard Riemann. Through them, Dirichlet's quiet genius spread further, becoming embedded in areas he never directly worked on. The true measure of Dirichlet's impact lies in how invisible it has become. His ideas are no longer seen as innovations, but as necessities. Modern textbooks build upon them without comment, assuming their validity as obvious. This is the highest compliment mathematics can offer. When an idea becomes so natural that it no longer needs justification, it has reshaped the discipline at its core. Even outside pure mathematics, Dirichlet's concepts quietly operate. In physics, engineering, computer science, and data analysis, his influence persists. Algorithms rely on convergence principles. Simulations depend on boundary conditions. Signal processing uses analytical tools refined by his rigor. These applications rarely mention his name, yet they rely on his intellectual foundations. In reflecting on Dirichlet's quiet genius, we learn an important lesson about lasting influence. True impact does not always come from loud breakthroughs or dramatic narratives. Sometimes it comes from patience, clarity, and the courage to demand precision where others accept approximation. Dirichlet's genius was not in dazzling the world with spectacle, but in giving it tools so reliable that they became invisible. His life shows that the deepest contributions often work silently, shaping thought from beneath the surface. Dirichlet did not just add to mathematics. He stabilized it, strengthened it, and prepared it for the future. Every time a mathematician relies on a clear definition, a rigorous proof, or a well-posed problem, they are unknowingly paying tribute to the quiet genius of Dirichlet, whose ideas continue to guide the discipline with calm and enduring authority. Dirichlet's lasting legacy as the true architect of number theory is one of the most powerful yet understated stories in the history of mathematics. His work did not merely extend number theory. It reshaped its foundations, transforming it from a collection of elegant puzzles into a rigorous, unified discipline. Long after his lifetime, the structures he designed continue to support some of the deepest mathematical research in the world. This enduring influence is why Dirichlet is remembered not just as a contributor, but as an architect whose blueprint still defines the field. Before Dirichlet, number theory was rich in results but poor in structure. Mathematicians such as Fermat, Euler, and Gauss had produced remarkable theorems, yet the field lacked a systematic framework. Many proofs relied on clever tricks, intuition, or special cases. Dirichlet recognized that without solid foundations, progress would remain limited. His vision was to give number theory the same rigor and conceptual clarity found in other branches of mathematics. This vision became the cornerstone of his legacy. One of Dirichlet's most important architectural contributions was the introduction of analytical methods into number theory. By linking integers with functions and infinite series, he created a powerful bridge between discrete and continuous mathematics. This approach allowed number theorists to study numbers through patterns and structures rather than isolated calculations. His famous theorem on primes in arithmetic progressions stands as a symbol of this new architecture. It demonstrated that deep truths about primes could be uncovered using analytical tools, setting a precedent that continues to guide research today. Dirichlet also established standards of rigor that became permanent features of number theory. He demanded precise definitions, logically complete proofs, and clear assumptions. This insistence on rigor changed how number theorists worked. Problems were no longer approached with informal reasoning alone, but with carefully constructed arguments that could withstand scrutiny. As a result, number theory matured into a discipline capable of supporting long chains of reasoning and complex theoretical structures. Another aspect of Dirichlet's legacy lies in the conceptual tools he introduced. Dirichlet characters and series provided new ways to encode numerical information. These tools allowed mathematicians to detect hidden regularities in the distribution of numbers, especially primes. Over time, these ideas evolved into entire branches of mathematics, including analytic number theory and algebraic number theory. Even today, researchers exploring the deepest mysteries of numbers rely on frameworks that trace directly back to Dirichlet's innovations. Dirichlet's influence extended beyond his own work through the mathematicians he inspired. His teaching and intellectual leadership shaped a generation of thinkers who carried his architectural vision forward. Bernhard Riemann, in particular, expanded Dirichlet's ideas into new dimensions, exploring the complex plane and uncovering connections that still define modern research. Without Dirichlet's foundational work, such advances would not have been possible. In this way, his legacy is not confined to his own achievements, but lives on through the minds he influenced. What truly defines Dirichlet as the architect of number theory is the durability of his ideas. Mathematical fashions change, but his principles remain relevant. Modern research in prime numbers, cryptography, and arithmetic geometry continues to build upon structures he helped establish. Even the most advanced theories often rely on methods that reflect his approach, combining abstraction with rigor and analysis with arithmetic. Dirichlet's architectural role also extends to how number theory interacts with other fields. By connecting numbers to analysis, he opened pathways between number theory and physics, computer science, and information theory. Today's cryptographic systems, which protect digital communication worldwide, depend on properties of numbers studied within frameworks that Dirichlet helped create. This practical relevance highlights the strength of his architecture. It supports both theoretical beauty and real-world application. Despite this immense impact, Dirichlet remained modest and focused on substance rather than recognition. He did not seek to dominate the field, but to stabilize and strengthen it. This humility is reflected in the quiet endurance of his work. His name appears in theorems and concepts not as decoration, but as acknowledgement of genuine foundational importance. Dirichlet's legacy also teaches an important lesson about progress in knowledge. True advancement often comes not from dramatic leaps, but from careful construction. By laying strong foundations, Dirichlet ensured that future mathematicians could build higher and explore further without fear of collapse. His architecture allowed number theory to grow into one of the most active and profound areas of modern mathematics. In the end, Dirichlet stands as the true architect of number theory because he designed the discipline to last. He provided it with structure, rigor, and unity, transforming it into a field capable of endless discovery. His influence continues to shape how mathematicians think about numbers, patterns, and proofs. Every modern exploration of primes, every deep theorem about integers, and every new connection between arithmetic and analysis rests upon foundations he helped lay. Through this enduring framework, Dirichlet's legacy lives on, guiding mathematics with quiet strength and timeless relevance.